Hey everyone, this is Kai. What I want to do in this video is to show you how you use the fodMC code and especially what output the fodMC provides, which you should always double check to make sure that the generated FOD guess makes sense. So we go into the examples folder and you will see 4 files. First of all, clean.sh does nothing else but cleaning up this folder. So it removes cluster, furmorp, and nuc_fod, which are the output files generated by the fodMC code, as well as the xx database file, which is an additional input file. I will get to that in a second. The README file, as usual, explains the folder and all the files themselves. What you should realize is that the examples folders is constructed in a way that you should run the code here and modify your input in order to generate output. So all of that you should do in the examples folder. Run.sh is a bash script for the execution of the fodMC, and I will show you that in a second. You can simply say bash run sh and you will run the code. The system file is your input file, where only the very first geometry is calculated and everything after an empty line will be ignored, which enables you to store as many inputs in one file as you want. The xx database file contains information about the atoms, mainly about the number of FODs or electrons, as well as the corresponding radii of the shells of each atom, which is mainly used for the generation of atomic gases, as well as for the generation of core FODs, where these information are read from this file. Usually you do not have to modify this file, just use it as is. If you modify it, you should know what you're doing. Clean.sh, I already explained that. And then we come to a very important point, which is visualization. You should always visualize the generated FOD guess. And for example, you can use the GUI from ASE to do that, and I will show you how that is done. Run.sh is the execution bash script, which will do the following. It'll define in which folder the fodMC main directory is, which is one folder up from where you're in right now. Then it'll tell you where that is. It'll copy the newest xx database file from your source folder and then executes the fodMC executable from the source folder. So this is all that is happening in here. And then for the system file, I will only focus on the very first example given here, which is the water molecule, to make you familiar with the input structure and especially with the output that is generated. The input structure is constructed as follows. The very first line is the number of atoms in your system. Everything else in the first line is comment and will be ignored. The second line is the used units, which could be angstrom or bohr. And then you have an XYZ file structure that is the element specifier, here oxygen, hydrogen, and hydrogen. And then 3 floating point numbers for x, y, and z coordinates. After that, you have another comment line, which I here call conmat, after which you can specify specific bond orders or lone FODs for atoms. In the case of H2O, you don't have to do anything, as the FODs for this molecule are generated automatically. And then you can run the code. And I'd like to go through the output on the screen first, which gives you the first indication whether the generated gas you have is meaningful or not. On bond information and lone FODs, you will see information for each atom and its corresponding bonding partners. So oxygen in this case with atomic index 1 is bonded to hydrogen with atomic index 2, and they have a bond pattern of 1, 1, which means there's one up and one down FOD in that bond, which we characterize as a single bond. The same is true for the oxygen bonded to the hydrogen with atomic index 3. We have the same bond pattern of 1, 1, so we have another single bond. So in summary, for the oxygen atom, we have 2 up and 2 down FODs in the bond. And in addition, the fodMC generated 2 up and 2 down FODs as lone pairs. For hydrogen of atomic index 2, we only have a bond to the oxygen atom. The bond pattern is again just the single bond. So in summary, for hydrogen we have 1 up and 1 down FOD in the bond and no FODs in the lone pairs. And in this case, of course, the last hydrogen has the identical information. So everything here basically corresponds to the chemistry of your system, so you should always double check that the bond pattern and the lone FODs per atom make sense. Afterwards, the fodMC will tell you what kind of molecule is used to generate FODs, in this case OH2. This is just a sanity check. And afterwards we check the physics, let's say, of the molecule. First of all, we have charge, which gives you the total charge of your system. In the water molecule, which is charge neutral, this has to be 0, and this is fine. Spin, given here as 2s, is the number of up FODs minus the number of down FODs. Again, in this case, the spin is going to be 0. These two numbers you should always double check to make sure that you do not introduce artificially some charge or some spin in your gas. In addition, we have an approximation for point charge dipole, which simply takes the molecular geometry and the FODs and assigns each FOD with a point charge and computes from that a dipole. Now this is probably more important in very symmetric systems where the dipole in certain directions needs to be 0, as can be seen here for the y direction. In the end, we have the computational time, which the fodMC took to generate this gas. So all of this information on the screen should be used as a first indication of whether the gas you generated is correct or not. And afterwards, you should always make a visual analysis of the generated gas. Again, I'm going to use the ASE GUI, and I'm going to guide you through what we see here. What we have here is your water molecule. The red sphere is the oxygen atom, the 2 white spheres are hydrogen atoms, and as you can see, in between each hydrogen and the oxygen atom, we have 1 X and 1 helium, which are the characterizations for up and down FODs. And these are exactly between the hydrogen and the oxygen, so these characterize our single bonds. In addition, the oxygen has 2 pairs of up and down FODs which are not in a bond, so these characterize your 2 lone pairs. And what's more, we have 1 pair of up and down FODs at the core of the oxygen, which identify the 1s orbitals or the 1s FODs. So this is a picture that makes sense for the water molecule. So after checking all the output that is given by the fodMC, you can use this gas to run a flow-C calculation. This is it for this video. Thank you very much.